Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Up to this point, when we have analyzed situation with forces, the forces have always acted on the center of the mass of the object. That's, for example, when we've been drawing free body diagrams. But that is not necessarily the case. Here I have a lever that is been acted by force F on its other end, and it's been pivoted at the other one. So because the F doesn't act on the center of the mass, then in this case the object would start to rotate, even if it wasn't pivoted at the point. So in either of these two cases, we need some other tools to analyze this movement and how does it produce, or how does force produce angular displacement or angular acceleration. But first, let's divide this force into two components. So it has the component along the axis of the lever, so that is called F radial. And then it has the tangential component that is perpendicular to this. So this is F tan. And it is clear from this figure that this radial component is not going to make this lever rotate, it just pulls on it. So the only component that can produce any kind of angular motion or rotational motion is the tangential component. And if this is the angle phi, which is the angle between the force and the directional vector of the lever, we call it phi. In this case, the only component doing force is the opposite one. So, okay, let's let it out of the closet. So, torque is defined as the component that can produce angular motion, the tangent one, multiplied by the distance from the pivot point. So this is generally called R, like this. The further we are from the pivot point, the easier it is to accelerate this object. And you have this experience from real life. So what is F tan? Because we have the angle phi there, the tangential is the opposite one, so it's going to be just the magnitude of the force F times sine theta R, like this. So the angle between the lever and the force definitely matters, as does the magnitude of the force and the distance from the pivot point. Another way to think about this is to see how far is this so-called line of acting from the pivot point. So the shortest distance is the perpendicular one, like this. If here's angle phi, so we also have the angle phi here. And let's call this L. This is in fact called the lever arm length of this force. So we can also say, first of all, L is going to be sine of R, sine theta times R, the hypotenuse. So we can also express this as FL, because L equals sine phi times R. And these are the forms, or various forms, that one can use for calculating the torque about some pivot point. There is one more, however, and in fact it's the most important one, the most formal one. If you look at this form, Fr times sine theta, or sine phi, phi is the angle between the two. This is in fact if you remember from the vector calculus, the cross product of these two vectors. Or I back up a little bit, it's the other way around. So, and the order does matter when we write them in the vector form. So it's a cross product between the directional vector r from the pivot point to the point of where the force acts. So here we have vector r in our case, and here we have the F. So the torque is also fundamentally a vector quantity. What is the direction of the torque? So we have to use the right-hand rule. So we point our fingers along the direction of r, that is to the right, using our right hand, and then we curl them towards F. And now you see that your thumb wheel should point you in the face or out of the screen. So that is the direction of the torque. The direction of the torque is aligned with the axis of rotation, as you see. So we might even call this torque Z, because it's about Z-axis, for example. So what can we do with the torque once we have been able to calculate it? I already mentioned that it produces angular acceleration. And to be more precise, let's say we have some torque, so it definitely produces angular acceleration. The higher the torque, the larger the angular acceleration, alpha. And we have some proportionally constant, and that is in fact the moment of inertia of the object, like we saw in the previous videos. The moment of inertia is the equivalent of mass in the linear motion. And to complete this, we have to have the net torque acting on the object to get this relationship for angular acceleration and torque. So this is the rotational equivalent of Newton's second law, where we have the sum of forces equals linear acceleration, and the proportionality constant, or the measure of inertia, is mass. In rotational motion, it's the moment of inertia. And we can call this C if we like, because it's a torque about axis Z, for example. Let's also box this formula or formulation, because that is equally important. And let's see how these two work together. So let's calculate an example based on the situation that we have here. So the length of the shaft, let's say it's 1 meter. Then we have force with magnitude of 10 newtons. Oh, the units of Newton, or torque, or by the way, force times distance, so it's going to be Newton meters. And then the angle phi between the direction of the rod and the force, let's say that's 30 degrees. And what else? Mass of the rod, 2 kg. So like this. So first of all, let's calculate the torque produced by this force about the pivot point. So torque, which one should we use? So we know F and we know R and we know the angle, so let's go with that one. So F times R times sine theta. So 10 newtons times distance, or the length of the rod, is 1 meter, times sine of 30 degrees, and that's in fact 0.5. So we get 5 Newton meters of torque when this force is acting at this angle and at this distance. And then we would like to solve for the angular acceleration experienced by this rod. So we go from the other expression, so net sum of the torque equals this more like this, and we are rotating about the z-axis, so that's moment of inertia times alpha, and we solve for alpha, so we get the net torque about z-axis and the pivot point divided by the moment of inertia. The net torque, it's just the one produced by the force F about the point that we calculated, so that's just tau. And the moment of inertia of the slender rod that has been pivoted by the other end, we calculated that earlier, so we can also look it up in the table. So that's 1/3 over ml squared, where L is the distance or the length of the rod. So we have 5 Newton meters divided by 1/3, mass 2 kg times the length of the rod, that's 1 meter squared. So what do we get? Value wise we get that's 15 divided by 2, so that's 7.5. And let's see what happens with the units. So we have Newton meters, that's Newton is kg, m divided by second squared and times Newton from here, and then we get kg times m squared. So kg's go away, m squared go away, so we are left with 7.5 1 over second squared. So 7.5 radians per second squared is the angular acceleration in this case. In the example, I will talk you through how to use this vector formulation. And it is not just a mathematical curiosity or formalism. It will become really important if you try to understand the operation of gyroscopes, for example. The way they rotate seems to defy common sense, and they will continue to do so if you don't go through the trouble of understanding the vector formulation. So we will have a look at that one later.